Hello dear friends and welcome to this week's challenge. So this week we are going to design a audio amplifier. So the audio amplifier that we are going to be designing this week shall be supplied by two power supplies um, with a 1.5 voltage tolerance for the power supply. The audio amplifier shall use TLV9301, which is an operational amplifier. The audio amplifier shall be able to manage stereo sound, so you will have two audio inputs. The audio inputs shall not exceed a voltage range of plus minus 500 millivolts, so that we put the signal in a plus and minus voltage range. The audio amplifier shall have high input impedance, so will not disrupt the circuit providing the signal, such as a phone or signal device. um, and this high impedance here, it's considered can be the impedance of the operational amplifier. The audio amplifier shall be able to filter input signal and remove signals lower than 0.2 Hz, so we should avoid DC voltage here, and above 20 kilohertz. The audio amplifier shall supply a 8 ohm speaker for each output. The audio amplifier shall be able to output at least 25 watt power for each channel. And the final one, the audio amplifier shall be in class AB. This means that it will have a leakage current between the high side and the low side transistors, and the leakage current shall be no more than 20 milliamps from driven from the input. Okay, so now I will start with the design. And if you want to try this design on your own, please feel free to pause the video now and let's compare designs in the comments. Thank you. Okay, great. So let us start with the hardware architecture for the audio amplifier. Because I've mentioned that we are going to use a two power supplies with 1.5 plus minus 1.5 voltage tolerance, and we need to provide about 25 watt power for each channel. I decided to go with a 19 volt power supply. It can go to 19.28.5 volts power supply positive, and minus 19 volts negative. Why did I choose this particular voltage level? First of all, there are available power supplies for this. Second of all, TLV9301, the operational amplifier that we have to use, has a maximum swing of or maximum supply of plus minus 20 volts. So the advantage is that we don't have to create a special um, lower voltage power supply in order to use the operational amplifiers. Okay, for the signal inputs, I have added a decoupling network for each of the inputs. The decoupling network has the role to remove any DC signal from the input, and the AC signal is then fed into a operational amplifier. So the first operational amplifier stage, which I decided to use a times 10 amplification for it. Then we're going to go through a filtering phase where we are going to use a low pass 0.2 Hertz filter, and this is a high pass 0.2 Hertz frequency, and low pass for 20 kilohertz. So this means that everything above 0.2 Hertz will go over, and everything above 20 kilohertz will go over. Okay. Then we go into the second operational amplifier op-amp stage, where we have an amplification of 2. So in total, we will amplify the input signal by 20. And this second operational amplifier stage will feed everything to a final stage biasing. So because we are going with an AB class amplifier, this means that for the driving stage in an AB amplifier, you will see that there is a constant current flowing from the power supply to ground in order to keep the both transistors uh, opened, so that there would be no distortion when crossing 0 volts from the plus and minus power supply. Okay, and then this final stage biasing will then power the driving stage, which will then, because this has a constant leakage current going through it, it would not have a distortion when passing 0 volts. But we will analyze this, and we can see how we can play with this final stage biasing, and then everything is fed to a output speaker. Okay, great. So let us start LT Spice and continue with the schematic there. Okay, so let's create a new schematic. And for the schematic, let's first add the power supplies. So let's go here, select voltage. So let's place a voltage power supply of 19 volts. And let's use 50 milliohm resistance, which is quite often seen in these switching power supplies. Okay, so let's copy this power supply and duplicate it here, and with this we will create the differential power supply, the differential voltage levels for the operational amplifier. And in order to make the schematic look even better, I'm going to go here, label net, and then I'm going to call this one plus 19 volts, and the one below I'm going to call minus 19 volts. Great. So this means that we have solved the power supply block. Now we have to continue with the coupling blocks and the amplification block. So let's start with the signal generator. So for the signal generator, let's use a sine wave of 500 millivolts, as we said in the specification. For the frequency, we can use like 10 kilohertz, and it's a sine wave at 10 kilohertz. Okay, and for the coupling, we are going to use a capacitor here that will create or will isolate um, the DC voltage from the power supply, or from the signal generator here, from the circuit. So I'm going to just place this capacitor here. Let's go with a 100 nanofarads capacitor here. You can create or calculate this frequency or the impedance for this capacitor at a certain frequency by using the impedance calculator formula 1 over 2 pi CF, where you can get the output frequency for this capacitor depending on the sine wave. You can calculate at different frequency values how much this capacitor would have as an impedance. Okay, and then let us also add a resistor to ground here, just that we sink some current, because here we would have a very high impedance going into the operational amplifier, and we don't want this input to be quite noisy. Next, let's start working on the first amplification stage. So for the first amplification stage, we said we are going to go with a 10 times amplification for the stage. So let's add the operational amplifier. Let us move it a bit here so that this syncs with the output from the capacitor. And let's connect the power supplies here. I would also like to add here two capacitors for each stage, just that we make the design a bit more realistic. So these capacitors should be placed as close as possible to the supply pin here. So I'm going to put here like a 10 microfarad capacitor and a 1 microfarad capacitor here, just that they are 10 uh, decades apart, so that we have some filtering here. In case we have noise on this line, these capacitors will filter it before it goes into operational amplifier. So this would be a priority when we are going to be routing the circuit. These two have to be close to the pins of the operational amplifier. And let's do the same for the negative um, for the negative supply here. And let me connect the ground. Let's see if this changes automatically. Yes, it does. So let me connect the other line. Okay, and let us connect this to the negative supply voltage, which is minus 19 volts. Okay. Great. So this power supply should be able to amplify my signal 10 times. Okay. So as we've discussed in the operational amplifier video, let us take a resistor here and a feedback resistor, and let's make um, uh, the difference between this input and the other one 10, and we also have a 1 from the calculation, so this means that it's going to be about 11 the amplification here, but it's not going to bother us that much. Okay, and let's connect the output, and here we are going to connect the ground. So as we said, one would be 1 kilo ohm, and the other one, let's say 10 times bigger, 10 kilo ohm. If we want to be precise, so we said we were going to build this to amplify 10 times, so this would be 1 kilo ohm plus 9 kilo ohm. For more information regarding operational amplifiers, amplification, with the negative feedback, please see our operational amplifier video where we explain how this is calculated and how simplify how to simplify this calculation and get good engineering ground rules here. Okay, so next we have the filtering stage. So for the filtering, let me rotate this a bit. We have one capacitor, one resistor, and then another capacitor and another resistor, because we want to have a band pass value here. So first of all, the high pass filter. Let me rotate this resistor because I don't like how it was initially placed. So for this, let's choose a 220 nano capacitance here, and let's put a 10 kilo ohm resistor. And for um, the high pass for the low pass filter, let's take maybe a 330 pico farads capacitor and a 100 kilo ohm resistor. So with this R5, you can also you can also control the volume here. So if you can replace this with a potentiometer, this could be an option. Just remember that if you are going to replace add the potentiometer here, would be great. Let me let me place it a bit better so that we can also add maybe volume. It's not in the specifications, but it's a good thing to have. So you can add here a maybe 1 kilo ohm resistor, and here 100 kilo ohm, and this can be the potentiometer. And then based on this, you can pull down the signal and mute the input signal from the first amplification stage. Okay, great. Now we have to go to the next stage of amplification, and I'm going to copy all the parts here, and I'm going to place them here. Maybe delete some components like this one here. Okay, and I'm going to draw and connect the signal here. So now we have a input from the filtering stage. We are here in the diagram, so we did the first amp stage. Now we're in the second operational amplification stage. This has an amplification of ×2. So let's build this. So here we have a ×2 amplification. This means that we can take maybe a 20 kilo ohm and a 10 kilo ohm resistor here for the feedback. One thing that we have to remove here is the feedback network. So the output from the operational amplifier has to go through the biasing stage, go through the driving stage, and then come back as feedback to the operational amplifier. Okay. Going forward to the biasing stage. So for the biasing stage here, we are going to use some transistors. I'm just going to place some standard transistor, but these can be changed further on in the development stage. So here, let us pick like a 500 milliamp transistor here. Let's see if I can find my favorite BC 87040 from NXP. This is a quite good operation NPN transistor. And let's bias it, let's say 1.5 kilo ohm, and on the other side let's put like 500 ohms, just that we kind of keep it open. Okay, good. So let us place and connect the biasing stage here. Okay, and so the biasing main role is to keep the transistors open. This is their main role. Always keep the end phase, the end stage open. Okay, and we would need some resistors here, just that this phase goes to the correct voltage level. So here let's put a 4.7 kilo ohm. Here let's put 4.7 kilo ohm, and this should go to the supply, or 19 volts, and this should go to minus 19 volts. Maybe I can move these a bit low because I don't want the traces to intersect. I even hate it here that they intersect. So let me connect this one here, and I'm going to connect this one to minus 19 volts. Okay, so now we've done the biasing. Last stage, we have to drive the end phase here. So let's place some driving stage. So put an NPM on the top side. Here we would need a resistance to drive this NPN, and then we would need also a resistor to drive the gate to. I don't like to put, some developers put like zero resistance here. I always like to have a limiting resistor here, maybe a 50 ohm resistor, just that I don't short circuit here by accident in the normal function of the amplifier. Okay, so let me connect this to the supply. Connect the transistor in the circuit. Okay, great. And last but not least, we will need a PNP transistor, and we have one here. This PNP transistor shall drive this PNP transistor shall drive the speaker on the output, and I'm going to connect this here, and the base to the collector of the driving transistor. Okay, and the driving transistor to the emitter, just that the circuit functions in the following way. So when we want to drive this PNP transistor, this allows the base to go to directly to the supply, or allows a voltage, a current to go to the um, to the emitter. So when this transistor conducts, this transistor should also conduct here, because we're pulling everything down. Okay. Final stage is to do the same for the low side. Let me add a now here we have the opposite. We have a PNP transistor here, and let me rotate this. Okay, so we have a PNP transistor here. Have to connect it same here to the biasing circuit, because the biasing circuit will open these two transistors, Q2 and Q4, and opening these two transistors will also open Q3 and Q5, which will be most likely our last transistor, which is an NPN transistor. Okay, so Q5 is here. Hopefully I have arranged them to, okay, yes. Now we need a supply for Q4, so I'm going to put this here. And then what we also need is an emitter resistor here, similar as for Q2, so that we don't accidentally short here. And if we short this, then it will fry the end stage. And I know it's fun to see, but yeah, nobody wants to be anxious about starting an operational amplifier. Maybe it blows up. So Yeah, it's no fun at all. Okay, and here the okay, and connecting the last the final driving stage here. Okay, so here we've placed 100 ohms, and on the other side 50 ohms. Okay, great. So our circuit is almost done. All we have to do is connect the high side with the low side, and for technical purpose, we need to put a 8 ohm resistance on the output here, just that we see how the circuit functions and how it would better work with a load. In reality, this is a coil here. This 8 ohm is the coil that is driving the actual speaker. So you would have also inductance here. So this would be inductive behavior for this resistor. Okay, so let's recap a bit because we also need to do some tuning. Before we recap, let's set the transistors. So as I said, I really like these BC8 transistors. So let me see if I can 870-40. This one, and the equivalent for this is 870-40. Okay, and for the final stage, I have no preference for transistors, so we can pick and choose whatever we want. It doesn't actually matter. Let me just reorganize this that it doesn't overlap here. Okay, so end stage transistors. Let's go to pick a transistor here. And what we know is we're going to be driving about 3 amps through it. So let's look through for transistor that can handle 3 amps, and also maybe a supply of 30 volts, just that we're on the safe side here. And on the other side, the same. So let's look for a 3 amp and 30 volts. I'm going to choose this one. Okay. Okay. So going back to the start, so that we discuss a bit the circuit. So the differential power supply outputs plus 19 volts and minus 90 volts. The input signal, the sine wave, which simulates the audio amplifier, is set at 500 millivolts with a 10 kilohertz frequency. The isolation capacitor here that will remove the DC component from the input here, 100 nano. It goes into an operational amplifier here with amplification of 10, then into a high pass filter designed to filter the low frequency signal, then into a low pass filter designed to filter the high frequencies. Here you can use also potentiometer that to control the volume and the output. Everything goes then into the second stage with the amplification of 2 here. I need to set these capacitors now. I see 10 microfarads and 1 microfarad, and here the same 10 microfarads and 1 microfarad. Okay, and the output from the operational from the second amplification stage goes into the biasing circuit. At the moment, the circuit is not biased at all. So I just put 1.5 kilo with 500 ohms. I'm not sure what would be the current going through the high, from the high side to the low side at all. We may have like 5 amps going. Maybe these transistors will blow up. That is when you are determining this biasing current. Always be careful to add a series resistance to the power supplies, just that you don't blow up the final stage transistors here. Okay, and how I'm going to test this, but we will do the biasing. I think the first thing that we're going to do is do the biasing before we see the amplification. So the biasing here has a leakage current flowing from the 12 volts to from the 19 volts to the minus 19 volts, and has the main purpose to remove the zero voltage distortion between Q3 and Q5. So this will allow a voltage here will slightly open Q5 and Q3, so that we don't have this zero voltage crossing issue. And the Q2 and Q4 are the driving transistors for Q5, just that they get the required current and function correctly. Okay, and the 8 ohm output resistor. Okay, first let us, so I think I've put values for all the components so that I don't get an error. First, let us run this circuit with zero amplitude and zero frequency. What would this mean? We will see now how much current we are driving through these two transistors from 19 volts to minus 90 for the biasing current. So let us run. Oh, uh, okay. Let's create a 10 millisecond simulation here, so 10 milliseconds, and run the simulation. And let us look here on this pin. Okay, ooh, 1.7 amps. It's a bit of 1.7 is quite quite much. Let us replace this to 1.1 kilo. First, let's start with 1 kilo ohm. Okay, so this means that at 1 kilo, okay, this is not done yet. Okay, so it's 2.5, so this is too low. Let's go to, so 500 watt, let's go to 800 ohms now. Okay, so like at 800 we have 3.7 milliamps, which is quite good. I think we can go a bit lower, so about 700. Let's see, just that they're quite, oh, too much, 200 milliamps. No, we're 750 ohms. Let's see, 40, it's still high. 750, 7, yeah, let's leave 800, and for 800 it's 3.8 milliamps. Probably it's going to be like 790 ohms. Yeah, let's see if this is a bit higher. Yeah, 6 milliamps is quite okay. We are well above our requirement here, not to have a leakage current greater than 20 milliamps here. So we are okay here. Okay, so let us now see how the circuit functions and actually see an amplified circuit, because now we just did the biasing. So let's do a 500 millivolts with a 10 kilo frequency. Okay, let us see. Okay, now we're seeing a current So, we're just measuring. Yeah, this is only the high side. I was wondering why everything gets cut here, but this is only the high side. So let us remove this trace here and connect the output, and it's a beautiful sine wave at 13 volts. Maybe we can increase the amplification here. Maybe let's make it 10 kilo ohms here with amplification of 11 here, and here 2 would be 22. But it's looking like, yeah, 15 volts. It's looking great. It's looking absolutely great here. Okay, and let us look here, because I said I'm a bit worried about the zero crossing. Here it's no distortion. Okay, okay. If the leakage current, so let us remember a bit this resistor, it's 790 ohms. Okay, if I put this resistor at 1 kilo as I had previously placed it. So 790 it's now, and I'm moving it to 1 kilo. Let's see how this voltage looks again. So it's still amplifying, but here at zero, oh, let me zoom in a bit. View, zoom to fit. Just want to see at zero here. Yeah, so here at zero, you see this crossing here. This is a distortion in the sound. So this means that you can see when one transistor is closed and the other one is still not opened yet. So this will cause a distortion in the sound wave. So let's go back to the 790, which were 790. Here you can use a potentiometer for this. You can use a potentiometer here for this R10 just to get this biasing structure under control. And here are 5 for the actual volume, so that you can control the volume of the amplifier. So let us run it again. It looks great. Perfect. Perfect. Okay, one last thing to do, maybe to check the output power. So I'm going to delete this trace. So we said about 25 watt power. So let me go here. This is the current going through this. It goes from 0 to 1.7 amps, and then back to minus 1.7 amps. By the way, when we are going to design this circuit here, when we're going to choose the power supply, we need a power supply that can double this current. So it will be about let's say 1.7 amps here, times 2. That would be 3.4 amps. Maybe we're going to go with a 4 amp power supply just to be on the safe side here for the 19 volt supply. But coming back to the output, so we're going to take this. So to calculate the power for this, we are going to use um, the um, the formula power is equal current to the power of 2 times the resistance, which is 8 ohms. I'm placing 8 ohms here. So the power goes to about almost 27, sometimes touching 27 watt power output for one stage. So this means 2 stages would be 27 times 2, which is 54. So we are also above the required, we're also above the required power output. Okay, that being said, I wish everybody that you have enjoyed this simple electronics challenge. Looking forward to hearing regarding your own challenges. If you have any ideas what you would like me to do as a electronics challenge, please write me in the comments. And wish everybody a great day and interesting challenges ahead. Thank you.